of wave is polarization. So when matter have these wave-like properties, it behaves like a wave. Then the particle nature of matter include Compton's effect, photoelectric effect, and then absorption and emission of radiation. So according to de Broglie, he said that matter can have wave-like characteristics as well as particle characteristics. Apart from this, de Broglie also arrived or brought what we call the de Broglie equation. We say that the wavelength of a particle is given as the Planck constant divided by the momentum of the particle. The symbols P or rho stand for momentum. Momentum given by the formula mass times velocity. So we can now say the wavelength of a particle given by h over mv. So this is the de Broglie's equation. So when we want to find the wavelength of a particle, either we use Planck constant over the momentum or Planck constant all over the product of mass and velocity of the particle. Okay, apart from de Broglie, another scientist that contributed to the quantum mechanics is Heisenberg. Werner Heisenberg. Heisenberg gave us what we call the uncertainty principle. Uncertainty principle, which states that it is impossible to predict simultaneously and precisely the position and velocity of a particle on an atomic scale. So this is the Heisenberg uncertainty principle. Heisenberg also developed a formula which is given as delta x, meaning or pronounced as uncertainty in position, multiplied by delta v, meaning uncertainty in velocity, is greater than or equal to the Planck constant all over the mass of the particle. That's the Heisenberg equation. We can say right in this one, delta s from applying m delta v greater than or equal to Planck constant. And in physical science, momentum written as p or rho is given by mass times velocity. So we can see right this equation as uncertainty in position delta s multiplied by uncertainty in momentum, which is m times delta v, is greater than or equal to h. So this is Heisenberg uncertainty equation. Okay, having understood that, we now move to another great man that worked on quantum mechanics. The man worked in Rutherford's laboratory. The man is another person called Niels Bohr. Niels Bohr gave us the atomic model of hydrogen atom. So the model of hydrogen atom was given by Niels Bohr. So what are the assumptions made by Niels Bohr in his atomic theory of hydrogen atom? The first one is in agreement with Rutherford's statement. He said that an atom consists of positively charged center with electrons revolving around it. So this statement made by Niels Bohr was a repetition of what Rutherford did earlier on before Niels Bohr. So if this is the nucleus of the atom, this this is the shell or energy level. Electron revolve around the shell or orbit, otherwise called energy level. So this statement is similar to the planetary motion that Rutherford described. Planetary motion, where the planet in the solar system, the planet, the sun is the center, and the sun corresponds to the nucleus, while the electron corresponds to the planet moving around. Planet, and this is electron. So that is Rutherford, Niels Bohr's first assumption, which is agreement with Rutherford's model. The question is this: why is electron not falling into the nucleus, since electron is negative charge and the nucleus is positive charge? Niels Bohr made us understand that the force that attracts the electron to the nucleus is called the electrostatic force of attraction, that would have pulled the electron to the nucleus. The force that pulls the electron out from the nucleus is called the centrifugal force. So according to Niels Bohr, the electrostatic force and the centrifugal force counterbalances each other, being equal. That makes electrons continue to move inside or around the shell. The second statement made by Niels Bohr is that the energy levels, or which are also called shells, are quantized. This statement is in agreement with Planck's statement or theory of energy quantization. That what it means that energy or shells are assigned to discrete amount of energy. Each shell possesses a particular amount of energy. And when electrons are inside this shell, electrons in shells neither absorb nor radiate energy. So for electrons to stay in the given shell, since each shell possesses the amount of energy, it can neither absorb nor give out radiation. As we have described in our fundamental class, this is the nucleus, these are the shells. So for electrons to stay in the shells, they will remain there without absorbing or emitting radiation. So that is one statement made by Niels Bohr, saying that the shell or the levels are quantized. The third statement made by Bohr is that electrons undergo transition from a higher energy level to a lower energy by emitting radiation. Now, you tell me that electron in a higher shell can move to a lower shell. This is the K, low M. It is possible for electron in the M shell to drop to the K shell. And when this happens, it emits radiations of light. Radiation of light in form of what's called spectral line. So this movement is called quantum jump. So if I should draw the shells in this form, this is K shell, L shell, the house M shell. Let's call the energy of K shell E1, this one E2, L shell, this one E3. So electron can fall from M shell to K shell, or from a higher shell to a lower shell, when it emits photons of light energy. Then, when electron emits this energy, it comes out as radiation. And the energy of the radiation is given by the difference between the energy of the higher shell, in this case the E3 for M shell, minus the energy of the lower shell, which in this case it is E1 for the K shell, which is also given by HF or the Planck equation. Then the fourth assumption made by Planck is that the orbital momentum, the angular orbital momentum of electrons are quantized. The angular orbital momentum of electrons in a shell are quantized. So he gave us the formula L, standing for the angular orbital momentum, given by NH over 2 pi, where N stands for the principal quantum number, referring to 1 integer values, 3, 4, 5, and so on. 1 for the K shell, first shell, LO shell, second shell, M shell, N shell, and O shell. As we have in the diagram, the first shell, the N is 1 here, N is 2, and N is 3, and so on. So, having done that, Bohr has also merits and demerits of his model. What are the merits of Niels Bohr's model? The merits is it fully explains the spectra observed in hydrogen atom and other light atoms. That's the first merit of Niels Bohr's atomic model. Second one is it gave the correct ground state energy level of an atom. So, for instance, we have the K shell, the LO shell, and the M shell. The ground state remains the lowest energy level of the atom. So, Bohr also has his demerits. The demerits are mainly that, one, he could not explain the spectra of complex atoms. Number one. Then he couldn't give the correct value. He gave an incorrect value for the angular momentum, ground state angular momentum of an atom. Okay. Then we'll have to talk about another man, Schrödinger. Schrödinger was a man that gave us the major breakthrough under atomic quantum theory, Schrödinger. This man developed a mathematical model with which he was able to calculate or determine what is meant by the atomic orbital. He normalized wave function to obtain atomic orbital of an electron. Atomic orbital is nothing but a region around the nucleus with the maximum probability of finding an electron. So in our next tutorial class, we're going to discuss the quantum numbers. Please stay tuned, subscribe to this channel, share, and make your comments. Thank you.